Hi there everyone. Before this video formally begins, I would just highly suggest that you watch the previous video where I go into depth about Newton's method, the theory behind it, the math, and the application of it to a specific problem. I don't really go over it again in this video, and so it'd be very helpful if you see the first video before watching this one. And with that, the video will now begin. Hey there, my fellow intellectuals. Dr. Kyle here with another video, and tonight I'm going to continue my review of Newton's method, and I'm going to apply it to solve a problem in celestial mechanics. So let's get started, why don't we? First off, this problem is going to involve the Lagrange points. The purpose of this problem is that we're going to find the distance of the L1 point in the Earth-Moon system. Now, Lagrange points are points of gravitational equilibrium where the forces between two massive bodies like the Earth and the Moon or the Earth and the Sun are going to perfectly balance so that a satellite can orbit where the centripetal force on that satellite is going to equal the gravitational forces exerted on it by the two massive bodies. So if we look at this picture here, this is the Earth Sun system. There are 5 points of equilibrium. The first 3 lie on the line connecting the Earth center and the Sun center, and then the L5 and L4 points form an equilateral triangle with the Sun and the Earth. So we're actually going to be looking at the Lagrange points that relate the Earth and the Moon, and I just looked it up. It's about 326,000 kilometers. L1, the Earth-Moon Lagrange point. And we're going to calculate this, and we're going to show this using Newton's method. So we already know what the answer is, but I just wanted us to have a target for us to aim for. Okay. And so how are we going to do that? Well, if we're going to be looking at the Earth-Moon system, I've drawn this very rudimentary picture here of the Earth and the Moon and the L1 point that we're going to search for. We're going to label its unknown distance by this lowercase r. And we're going to denote the distance between the Earth and the Moon by this capital R. Now, if we just think about this simple 3-body system where we ignore the mass of L1, or not the mass, but we just ignore the gravitational force L1 has on the Earth and the Moon, then we can just really focus on what the Earth and the Moon are doing to L1 as opposed to what the satellite at L1 is doing to the two massive bodies. I believe this is what is called a restricted 3-body problem, as in you're treating the third mass in the system just completely undermassive compared to the other two. So where do we start? Well, the first thing that would be good to do is to draw a free body diagram on this satellite. So of course there's going to be a pull from the Earth and a pull from the Moon, and they should balance at this point to allow the satellite to orbit the Earth in synchrony with the Moon. So this will always keep the satellite rotating at the same angular velocity as the Moon. And so to figure this out, we should write down Newton's laws. Remember Newton's second law, F equals ma, which in a circular orbit, this is equal to m times the linear velocity squared divided by the radius of the orbit. So we're going to measure the radius of the orbit with respect to the Earth's center. So the Earth's center is basically going to be our 0 point in this system. And I should have also written a summation sign because it's really the sum of these forces. And so the sum of these forces are going to be the force from the Earth, right? So just using the Newton's law of gravitation, it's Newton's constant g times mass of the Earth times mass of the satellite divided by little r squared. And I'm basically going to define things moving in the direction of the Earth to be in the positive direction and things moving towards the Moon to be in the negative direction. It works out either way, but I'm just going to write it like this for simplicity's sake. And so that's the Earth's force on the satellite, and then we have to write the Moon's force on the satellite. So m Moon, m satellite, and the distance between the satellite and the Moon is going to be this distance here. Now I've called the Earth-Moon distance big R, and I've called the Earth satellite distance little r. And so hopefully by looking at this picture here, you can see that the satellite moon distance is going to be big R subtracting little r. So I should write it like this: big R minus little r squared. And again, remember this is equal to mv squared divided by little r. And notice also that the satellite's mass can cancel out in all of these terms. So we're going to cancel that out here. If I can just write this in red. And so what we're left with is that we're left with the following equation: gme over r squared minus gmm over big R minus little r squared is equal to v squared over r. One last thing I'm going to write is that remember from intro mechanics that we can relate the linear velocity to the angular velocity, right? So the linear velocity and the angular velocity are related by the following equation. We have v is equal to r times omega. Omega is the angular velocity, r is the radius of the orbit, and then v is the linear velocity. Now this satellite is going to be in a synchronous orbit with the moon, so it's going to essentially rotate with the moon at the same rate as the moon orbits the Earth. And we know that the moon's orbit, I looked this up, is about 2.66, what is it, 2 times 10 to the minus 6 radians per second. Okay, so that's just something that was given in this problem that I'm solving here. But I'm essentially just going to rewrite this last term in terms of omega. Okay, and so if you write this in terms of omega, what you get is that v squared is equal to r squared omega squared, and then you divide it by this r down here. And so the right-hand term should just equal, what do we have here? So we take out 1 power of r, so this should equal r omega squared. Okay, so the equation we're trying to solve, I should probably write it a little bit more cleanly here. Let's just write down the final equation so we know what we're going for here. Let's see, r minus r squared is equal to r omega squared. Okay, so this is the equation we're trying to go after. Okay, this is what we are going to set up, because we're going to use Newton's equation, or Newton's method, I should say. There's already a Newton's equation in this problem, but Newton's method to figure out what the power, not the power, but what this value of r is. Now, the equation in r, because r is sort of nested, all around here, this is actually a quintic equation in r. If you tried to isolate r and solve for it, there should be an equation that involves an r to the 5 power, which there is no closed form solution for that. Because of that, we can't solve this by hand, but we can solve this numerically. Okay, so how am I going to do that? Well, I do need to do a couple of things here. I need to define a function that I can use Newton's methods for. First off, let's just write down some constants that we know. So let's get Newton's constant in here. 6.674 times 10 to the minus 11. So mass of the Earth is equal to 5.974 times 10 to the 24, I believe, kilograms. Yep. Mass of the moon is equal to 7.348 times 10 to the 22 kilograms. The big R, the Earth Moon distance, is known to be, what is it? On average, it's R is equal to 3.844 times 10 to the 8 meters, and then omega, which I mentioned earlier, is 2.662 times 10 to the minus 6. Okay. Oops. What happened here? Maybe I should just not write it like that. Is that better? Okay, yeah, you like that. Okay, so Python likes that. And what we have to do now is we have to somehow define our function that we want to solve. Because basically this equation right here, which I wrote down, if you just subtract r omega squared, ooh, that looks kind of ugly. Let me just do this instead. So if you subtract r omega squared to that side and set this equal to 0, right, you're basically trying to find the value of r that makes this equation true, right? What is the equation of r that's going to set this equal to 0? Okay, and this is going to be our function of r. Okay, so this is our function of r, and we're going to need to take some derivatives actually, because to do Newton's method, you need to know the derivative of the function. I need some more space, so I'm going to just zoom out here, and then I'll just get the paint bucket and I'll just drop that there. Okay, and zoom back in. Let's get back here. Okay, so I actually need to take the derivative of this function with respect to r before I can use Newton's method. So f prime of r, so gme r squared. So I'm going to go a little bit quickly here. This is just using the power rule. Gme to the r squared could be written as gmre to the minus 2. So I'm just going to use the power rule here. So it'll be 2 gme r to the minus 3. It was just going to be r cubed on the bottom. Then we have minus g. So basically we're going to have a chain rule going on here because we have a big R minus little r squared. So this term gmm big R minus little r squared, oh sorry, that's minus 2, becomes 2 minus gm r minus r cubed times, oh, negative, times a negative 1 because the minus sign of the little r right there. This should not be minus, this should just be minus 2. Okay, so that's what it looks like, but there's also a minus sign here, so it's still minus at the end, surprisingly. So this is minus 2g moon mass r minus r cubed. And then we take a derivative of this. This should just be omega squared, right? Because we just have one linear power of r there. So I have the function, I have its derivative. Okay, great, because now this is what we need to apply Newton's method like in the last video. So this is the function we need to write. So I'm going to define f of r to be the following. It's going to be, let's see, f is equal to, so it's g times me times little r raised to the minus 2, right? And then minus g times times r minus r to the minus 2. And then we have, I believe it's just minus r omega squared. Yes. Minus r times omega squared. Okay, return f. And then I'm going to define df dr of r, which is just going to be df dr is equal to, it's basically going to be, just we wrote it down here, right? So it's minus 2gm. I'm just kind of concerned about this. Maybe I should just parenthesize this. I'm not so sure. I'm just getting a little paranoid that my things are not going to work right, so I'm just overly protecting my variables. That's probably unnecessary, but better safe than sorry. So this is minus 2 times g times me times r to the minus 3. This is still a negative, so this is 2 times g times m times big R minus R minus 3 minus omega squared, right? That's just it. Yeah, okay. Okay, so that's the derivative, and then we'll return dfdr. Okay, so we've got the function, we got the derivative. Newton's method, right? Newton's method uses, so it uses the following update rule. Let's see what we got here. I have to remember the equation. I did not write it down. The guess, right? X new, right? It goes something like this. X new is equal to X old minus F of X old divided by F prime of X old. Okay, so that is what we have to program again. So we need to come up with some sort of tolerance that we want to get the answer accurate to. So let's just say accuracy is, I'm just going to say 1 to the minus 5. I think that's reasonable. Yeah, for sure. 5 decimal places of accuracy. Why not? And we need to come up with an initial guess, actually. So what's an initial guess? Well, we know what the answer is, actually, so I don't want to cheat too much. So we're saying, so it's 326,400 kilometers. I should be able to do this in my head, but let's just see. That's a lot of meters. 326 million meters. Oh wow, that's a lot of meters. So what if I just guess maybe something like 200 million? Okay, is that too close? I'm gonna go 200 million. So 200 million is 2 times e to the 8. So let's say our guess is equal to 2 e to the 8. And then we need to start a loop. Let's do a while loop. Let's define something like, let's say delta is equal to 1.0. So this is going to be the variable that measures the ratio of this. And so when we find the root, it should be less than, it should achieve this accuracy if it converges. So anyways, let's go here. While abs accuracy, no, sorry, while abs delta is greater than accuracy. So we're saying, well, as long as delta 1 is greater than accuracy, so this is going to be true, right? 1 is greater than 1 times e to the minus 5, or 10 to the minus 5. We want to do the following. Delta will equal, I see, f of our guess divided by df dr, our guess. And then we just do our guess is equal to minus equals, which is just equal to, our guess is equal to our guess minus delta explicitly, which I could have just written like this, minus equals delta, same thing. Okay, let's try this. Oh, wow. That's pretty good, right? 326,400, was that what the 326,400? Really? Seems a little bit off. Can I get another decimal place precision? 7. What if I change my guess? No, it hasn't changed. 326. That looks correct. But this is in meters, right? So converting it to kilometers. What do we get that in? So kilometers, 326,400, 326,045. Which, okay, I mean, that's not bad. How much is this divided by 326,400? Actually, that's really unnecessary, but 99.89%. No, pretty good. All right, I'm pretty satisfied. Looks like it works. So with that, that's all for me. I hope you found this video to be somewhat insightful. I know it took a while and I did not solve this problem beforehand, which is why I took my time. But I hope that seeing my problem solving style and seeing how I talk through a problem, how I think through a problem, and how I go from writing down the equations on paper or in MS Paint in this case and translating it into code in Python, you can sort of see how the gears are turning in my head and how I'm trying to formulate a logical solution to the problem. So let me know if you found this video to be useful. Like the video if you did. Comment if there's anything you'd like to say or mention, or if there's anything else you'd like to see. And with that, I will see you in the next video. So take care, everybody.